I totally forgot to restart the recording. So people watching the recording totally missed that solving of that exercise. Sorry about that. Anyway, I guess I'm having a bad day. Anyway, let's go on. Let's do this. We can do this. And let's go back to our PowerPoint. So this is where we were. So that's the problem we just solved. I apologize to those of you who are watching the recording. I totally forgot to restart the recording, and so you missed the actual workout, but you will get the final solution here. All right. The other piece of evidence that led to the proposal of quantum theory was the study of what happens when you run electricity through a sample of a gas. All right, we're going to talk about spectra. And these are different kinds of what we would nowadays call a neon tube, which is very, common in Vegas and places. There's a lot of lights and stuff, right? So essentially, you put a gas inside a tube and you run electricity through it, a certain amount of energy, and different gases produce light of different colors. And that's how you make a lot of so-called neon signs and stuff. Now, you can take now that light that's produced and study it through a spectroscope, which essentially breaks down the light. In this case, you see on the left there is a hydrogen lamp, and it breaks it down into its components. So let me show you a sketch of a spectroscope. So here we have our hydrogen lamp on the left, a slit to focus the light into a single beam that is now separated by a prism into its separate components, and then recorded either on a film or a screen. And what you find is what is called the emission spectrum of this particular substance. Now, because what we're analyzing is the spectrum of light emitted by the actual hydrogen lamp here, right? The hydrogen lamp here on the left. We call this an emission spectrum. That's what we have in here on the far right. It's interesting, if you put different types of gases in that lamp, not necessarily always hydrogen, you can get all kinds of things. You can see on the top there the helium spectrum, barium. On the bottom, you have the neon spectrum, the one that we're familiar with from neon signs. Notice that white light gives you what we called remember we called it a continuous spectrum, right here in the middle. And opposed to that, these other guys give us what are called line spectrums. We call this a line. Oops, hold on a second. Let me, that looks pretty messy. Let me use the pen here. Let me see if I can get my pen to work. So this would be a line. Spectrum. Sorry, like I said, my stylus doesn't work very well. And specifically, let's look at the one that we have for hydrogen here. All right, so here is again our sketch. And what I've done is I've taken that picture on the right and displayed it in big on the bottom. And this is what's called the line emission spectrum of hydrogen atoms. Now, scientists knew this, that when they broke apart the light emitted by a hydrogen lamp, instead of getting some kind of a rainbow, they got a line spectrum, and it consisted of 4 specific bands of light. And the big question was, well, why do you get this? The next slide is not on your handout set. Don't worry, you don't need the information. But basically, one of the things that some people did was they tried to come up with some equations that would predict the positions of these bands. In other words, the wavelengths of these lights. And different people, Johann Balmer basically did an empirical derivation. In other words, just basically a brute force approach that could generate the series of lines. And then essentially, Johannes Rydberg came up with a more detailed approach and generated what eventually became known as the wave number of each line. And here's the formula that you have in there. It says here, 1 over lambda equals R times 1 over N1 squared minus 1 over N2 squared. Now, what are N1 and N2 here? They were basically two numbers. So Rydberg basically we plug in numbers in here, and he could find the right numbers to fit in that would give you the correct frequency of the light on that spectrum that we studied before. So basically by plugging in numbers brute force, they could generate these four bands of wavelengths in here. And this was the value of the so-called Rydberg constant. RH was 109,678 inverse centimeters. But it still did not explain why you had this pattern. All they did was a brute force algebra approach, and they could come up with an equation that if you put the right numbers in, you could generate those four lines in the hydrogen spectrum. But there was no basis for it until along came Niels Bohr. Niels Bohr took a bold step in proposing a model that explained why you obtained that spectrum for hydrogen. And it's been known since as the Bohr model of the atom. All right. So I'm going to go up here back to our handwriting and torture you with some more handwriting here on our doc cam. All right. And let's see if we can get this to work. This is called the Bohr model. And you're familiar with it because some people still use this model to explain what atoms look like, even though they don't look this way at all. All right. So basically, the Bohr model proposed that electrons travel in fixed orbits around the nucleus. Sometimes it's been called the like a planetary or solar system model. In other words, if this is the nucleus, then you have an electron here, basically traveling in an orbit around the nucleus. And then another electron would travel in a different orbit and so forth. And the proposal was that each orbit has a unique energy and borrowing from the Rydberg and Balmer equations that have been done before, he figured out that the energy of orbit n would be minus a modification of the Rydberg constant. I'm going to put R sub b instead of sub h times 1 over n squared, okay, where n is, 1, 2, 3. In other words, the orbit number. And this constant RB is a constant in units of energy, 2.18 times 10 to the minus 18 joules of energy. So basically what he did was he now is going to try to make sense of the Rydberg equations from the point of view of an actual, let's say, an actual physical model. Notice that this model already predicts something. It predicts that each electron is going to have a unique amount of energy associated with it that depends on the orbit that it's in. There is no in between. So an electron is either in orbit 1 or orbit 2, but never in between. Much like the planets orbit the sun in their own particular paths, and they don't basically, basically stroll around all over the solar system wherever they want. They're kind of fixed. They're bound to specific paths. And that was essentially the novelty of this model. Again, I apologize for the blurriness here. I'm really sorry, but don't worry. You'll get all these pages later on properly placed, okay? Again, I'm really sorry about this. I did not anticipate this issue with my internet here in the house. Gosh. Okay, so let's see. I'm going to keep on going. Sorry, guys. Probably from what I say, you can pretty much put in the pieces together. So again, this is, by the way, this is n1 over n squared. Okay, that's a 2 in there that I try to write, but it's very blurry right now. So let's consider some scenarios. Let's consider n being to infinity and beyond. In other words, let's say this is an electron that's in an orbit very, very, very far from the nucleus. Well, at this value, 1 over n squared, this bottom number is so big that essentially this approximates a value of 0. And therefore, the energy of the electron at this point would be 0. And you go like, well, does that mean that it doesn't have any energy? No, it doesn't mean that because the energy we're talking about is an energy that depends not on the motion of the electron, but its position. In other words, this is essentially a potential energy, all right? This is potential energy. It's based on the position of the electron, in this case, the orbit. Okay, so let's say n equals 1, which is the lowest level possible. Notice there's no n equals 0. So this is the lowest level. And we're going to call it the ground level. Notice that here, 1 over n squared equals 1. And therefore, the energy of this electron is going to be minus that modified Rydberg constant. This guy to behave. Gosh. All right, we'll see how we can do this. Let's try n equals 2. Let me get this paper out of here. Okay, let's try n equals 2. Okay, so that means that the energy for orbit 2 would be minus this constant times 1 over 4. Or minus RB over 4. For n equals 3, the energy of this level would be minus RB over 1 over 3 squared, which is 9. In other words, minus RB over 9. So if you look at these numbers and you can think of, let's say that we're counting in units of this constant R sub B. What you see is that you are moving in a scale of negative values. Remember that for potential energy, negative is good. In other words, let's say the more negative a value is, that means the less work would have to be done, right, in order to move it in the direction, in a favorable direction to a natural attraction force. Remember, the electron should be attracted to the nucleus. The closer it is to the nucleus, the better the situation, the more stable, and therefore the lower its energy should be. This is similar to what we discussed in the previous chapter about the formation of bonds, and when you have a chemical reaction from reactants to products. So what we have here is a scale of values, all right? So let's redo this scale in the form of a picture now. And it's going to look like a ladder. So let's say that I start here. Again, we're going to get blurry again. all right? Let's say that I start here at n equals 1. Now remember, the energy of that was minus RB, right? So this is the energy. Sorry that it's blurry again. For a moment, it picked up again. Now, the highest amount of energy, the most positive, would be essentially at infinity, right? When the electron is essentially not even in the atom anymore. And that value would be 0. So that means that this is a scale that runs essentially in the negative realm all the way. So for n equals 2, you would be maybe like here. For n equals 3, you might be like here. You notice that when we're calculating, the fractions got progressively, less apart from the previous one. Let's say this is n equals 4, n equals 5, n equals 6, n equals 7. Notice that as you go higher and higher, the separation between the different orbits is less and less and less. All right? It's like a staircase. So the electron can be on any one of these steps, but it's never in between. All right? So the electron is in an orbit, but never in between. That means that the energy is quantized. So let's say that I have an electron here. This is called the ground state. And let's say that I now input some energy. So let's say that I input energy. If it is enough, I might be able to cause the electron to jump to the next step. Notice there's no room for the electron anywhere in between. All right. We would call this the excited state. Remember, it's a state that has more energy. But by more energy, we mean it's less negative, right? In other words, it's farther from the nucleus. It is not in as stable a possibility to interact with the nucleus as there was in the ground state. Because the excited state is not stable, or let's say it's less stable, the tendency is for the electron in the excited state to return to the electron in a ground state. But there's a problem with that. You put energy in, what happens to that energy now? Because you had to conserve energy, right? Remember we talked about the conservation of energy? So what happens to that energy now? It has to go somewhere. Well, the way that energy is released is in the form of a photon of light. And that photon is going to have an energy that is going to depend on its frequency. Cool, huh? So let's see what that energy is going to look like. So let's see what the remember we said I went from, let's say, an initial, from some state here to this state here. So this is, let's say, a lower orbit. This is a higher orbit. Oh gosh, sorry guys, it's getting creepy again on us. Sorry about that. Hopefully it'll pick up in the next few seconds again. And now it's gonna return. And there's gotta be a change in energy in there, which as always is final minus initial. All right. So let's see what that would be. E final would be negative RB times 1 over N final squared minus initial will be minus RB times 1 over N initial squared. But if we rearrange that, so not to have that many weird negative things in there, let's rearrange this as RB over 1 over initial squared minus 1 over the final squared. So notice, because in this example, the initial state is the higher orbit and the final is the lower orbit. Oh gosh, I'm having more problems here with this thing here. This is getting worse and worse. All right, sorry about that. I'm going to take us to the PowerPoint in a moment. So because we're saying that, you know, the initial state was a higher orbit than this one, then that means that 1 over Ni squared is lower than 1 over Nf squared. And therefore, the energy change is going to be negative. In other words, energy is being released. That is the energy that is going to be captured by our photon. And based on that value, we can calculate what is the frequency of that photon. All right, guys, let me do this. Let me get us out of this doc cam here and take us to an example here. And I apologize again. We'll see if we can fix this next time. All right, here we go. Where is our... Oh. All right, so we're talking about Niels Bohr. So let's look at this example here. What would be the wavelength of a photon emitted by a hydrogen atom when its electron drops from the n equals 5 to the n equals 3 state? All right, let's look at that formula we just had. And all we're going to do is we're going to plug in the values for R, and we're going to plug in the values for Ni and Nf. Remember, Ni is where it starts, it's the higher state, the higher orbit. N sub F, the final one, is the lower one. So if we plug in the numbers, remember the value of this constant. By the way, I think you may have may need to correct this. I think in your handout, it says R sub H, but I prefer to keep R sub H as a symbol of the original Rydberg constant and R sub B as the one that we use in Bohr's model, which is in units of energy. All right, so let's plug in the numbers. So essentially, initial state is n equals 5, so square root of it is 25. Final state is n equals 3, so square root of that is 9. So we have this here, and we can calculate to be negative 1.55 times 10 to the negative 19 joules. So one electron dropping from orbit 5 to orbit 3 would release this amount of energy, all right? That is the amount of energy that is going to be captured by a photon. In other words, this energy, because it was potential, it's not going to be kinetic energy. It's going to be emitted in the form of a photon of light. And the energy of that photon would be essentially whatever this transition generates, that is what the photon absorbs. So it's the negative of that. And it'll be Planck's constant times the speed of light divided by the wavelength. So we can rearrange the equation to solve for the wavelength, right? And now we put in the numbers. Remember, both H and C are constants. So in an exam situation, you'll be given these values. But of course, in your homework, you have access through this either in the appendix of the book, or if you have a hard copy book, usually in the inside of the back cover. Okay, so H is 6.63 times 10 to the negative 34 joules times seconds. Speed of light, 3 times 10 to the 8 meters per second. And we can see here that what's going to happen here is that we are going to be canceling out the seconds. We're going to cancel out the joules. The value of the joules, by the way, came from the transition. And so you're left in meters. And of course, you're going to want to convert that perhaps to nanometers, because that's what the question set up here. It's converted to nanometers, right? So let's see what that is. I'm not getting anywhere here. Oh, there we go. Sorry about that. I couldn't get my slide to move forward. So the result after you convert to nanometers is 1,280 nanometers. Now, if you look back at the scale, the range of wavelengths that we call visible light, we said it was between 400 and 750, right? So this is kind of outside that range. In other words, the photon that's being produced here is not in the visible range light, right? It's not in there. So if we look at that chart, we'll find that it's actually infrared. Now, this is transition. Remember that we said that as you go higher and higher in orbits, the distance between one orbit and the next one is smaller. That means that it's less energy released. And as a consequence, you would expect for the wavelength to be longer, in other words, less energy. But what happens in that case is all those transitions give us light that is not visible. In a similar fashion, any transition going all the way down to level 1, because that gap in energy between level 1 and 2 is so big, any one of those transitions would generate a photon of such high energy that the wavelength would be in the, ultraviolet range or something like that. It wouldn't be visible. So Bohr's model predicts that there's only a particular specific set of transitions that are going to give you just the right amount of energy to produce photons of visible light. And here's 3 of them. Essentially, the only transitions that allow you to produce photons of visible light are transitions into orbit number 2. So from 3 to 2, what you have there is you have a smaller gap than you have from 4 to 2, than you have from 5 to 2. And so as you go through each of these transitions, in this case from right to left, you can see that the farther away the electron is falling from back to level 2, the more energy is produced, and therefore the shorter the wavelength of the photon of light. The next one will be the level 6, from orbit 6 to orbit 2, and that one is going to be slightly a little more energetic than the one we're showing here in the violet range. So I don't have it in here, but the idea is that the Bohr model predicts that you can have these line spectra due to the transitions of electrons as they move from one excited orbit down to a less excited one. And mathematically, you can even calculate what the wavelength is going to be. And so Bohr's model was essentially the emblem of, the atomic structure for a couple of decades, right? Bohr even received the Nobel Prize. But unfortunately, as happens with many theories, when you started to apply it to helium and lithium and so forth, and atoms that had more than one electron in them, the model didn't work. Oh my gosh. So what do? Do we simply toss it? Do we toss it? No, we modify it. And that's why we're going to stop here. But in our next session, we're going to talk about how scientists came up with the idea that, well, if light sometimes behaves as a wave and sometimes as a particle, what about if electrons sometimes behave as a particle and sometimes behave as a wave? And that was the basis for launching what is called the quantum theory of the atom. All right. So we are going to stop it here. Again, I apologize tremendously for all these issues here with the internet connection. I'm really sorry. But again, you will have copies of all these handwritten sheets when I post the recording. Also, my apologies again, because when we came back from the break, I forgot to restart the recording, so you missed out one of the solutions to the problems. But again, you'll have the sheet with the final solution. Okay, I'm gonna stop it right there. And let's see. Let me see, I think there were maybe some comments on the chat here. Where did the negative sign go? Håkon, can you unmute your microphone and ask me exactly where that was? Which?
Yeah, it was on the word problem. God, English. It's on the word problem.
The one in the
yeah, the calculate wavelength in the
one in the PowerPoint.
droppings from from
okay.
the PowerPoint.
So let me go back. Let me go back there. Let me walk through
I noticed.
I think I know what you. I think I know what your question is.
Yeah, it's right there. It's on energy as photon equal to negative delta E.
Right.
And then when you change the thing, when you change to find for frequency.
So the energy of the photon is the negative of this.
Yeah.
But delta E is already negative. So the negatives essentially cancel out.
Okay. So
the energy of the photon
but does it ever?
I'm sorry?
Does it always be negative in that case then?
Well, remember what I said. Because typically the initial state is a bigger number than the final state, when you do the reciprocals here, turns this expression in parentheses here is always going to be negative. You can see it here, 1 over 25 minus 1 over 9, right? The second one is bigger. So delta E for a transition from a higher to a lower orbit is always going to be negative because you're losing energy.
Okay.
But because of conservation of energy, the photon captures that energy. So the photon is absorbing that energy. So it has a negative sign. It's kind of similar to what we did in calorimetry, where the energy that is gained by the solution is lost by the chemical reaction and so forth, right? So essentially, the energy of the photon here would be minus 1.55 times 10 to the negative 19.
Okay.
In that way, if not, you're going to get a negative wavelength, which is no such thing, at least not in this universe. Maybe in an alternate universe you can have that. All right. But thanks for asking. That's a good question. So when you guys solve these kinds of problems, be very careful with the signs. Okay. Don't dismiss the signs. Keep them in there until you're sure why your math has, eliminated one of them. All right. All right. I'm going to stop the recording.